So hello everyone, I'm Antoine Morvan, and I will present you some feedbacks from few Center of Excellences that have been working on porting codes to ARM and a bit of HBM too. So just a quick presentation of where I come from. So I come from Eviden. We mainly sell hardware and exascale computers nowadays. We have a bit of software environment for the drivers, a bit of management software. And on top of all of this, after we deliver the machine, we come with a Center of Excellence, for instance, in performance programming, where we help the developer that will face the machine we sell to exploit it best. So we work with industrial partners, we see on the top right, but also intervene in collaborative projects, national, European, and recently international with India and Japan. So in this context, with EUPEX in mind, the objective of the COEs is to make technology providers, academics and computing center work together, within Europe work together and prepare the code for Rhea 1, where we have two main objectives in mind. The first one is to assess the maturity of the ARM software ecosystem, so it overlaps a bit with work package 3 of the EUPEX. Make sure that the SVE vector instructions are competitive with what we have on the traditional x86 CPUs. And the second side is checking if the HBM that will be integrated in the Cycle CPU brings benefit to European strategic applications. Okay, so we'll quickly go over the 4 COEs where we have been working. So if you were attending yesterday's workshop on the COEs, there will be a bit of overlap there. So we have been porting code within the space COE. It is about astrophysical science. So here on the top left you see a list of the codes that have been subject of the COE. You can see all the partners. I will not go over it. It will take a while, and interaction between the centers, academics, and technology providers. Second one is CHEES. It's about say that seismic solid earth physics. So there are 3 main objectives. The one I feel the most interesting is the urgent computing. You have some earthquake somewhere and you want to know where the tsunami will reach before it actually reaches, so you can tell people to evacuate or go in safe position. So on the top right, you see the domains and a long list of codes also that have been subject of the COE. And again, a lot of partners within Europe, and again, computing centers, academics, and so on. The third one is MAX. It's material science, with again, a lot of partners. You can see here how the project was organized with co-design in mind for preparing codes and giving feedbacks also to the technology providers and a bit less CPU designers. Again, here you have a list of lighthouse codes that have been ported and we played with those codes. And finally, Easy Waste 3, it's a Center of Excellence for weather and climate applications. This is the one that the most part in. Again, on the left you see a long list of partners. So here there is a bit less code because we have been integrating them in a benchmark suite that's called HPCW, High Performance Climate and Weather Benchmark Suite. I will talk about this a bit more later. And during 26, we have planned to do some hackathon to make sure that the code runs efficiently at scale on Jupyter after it's delivered and ready to play with. Okay, so a bit back on what are the 2 main objectives on the exercise for the COEs to support on Rhea. So again, it's to check that the choice made by Rhea for choosing the Neo version 1 microarchitecture, so the ARM microarchitecture, and the SV instruction will behave efficiently, will deliver a good level of performance, that the software stack on ARM systems is ready, is working. I mean, it was not at the time. Spoiler, it is now. And the second point is checking how it behaves with the HVM. So how do you check that ARM is working and the SV is efficient? So basically, we were putting face-to-face some traditional CPUs with the usual software stack we have. So mainly after 20 years, 10-20 years of monopoly from Intel, so the code are running either with the Intel compiler or GCC. I mean, I will focus on CPU, I will not talk about GPU here. So yeah, the code were into what I would say, I don't know if it's written here, x86 dogma, that was the figure of style from NVIDIA guys. So we have to bring a bit the code out of the Intel x86 dogma and make it work on ARM. So it was possible thanks to the availability of new systems. So the first one was a bit of effervescence after Fugaku. So many people were buying A64FX to have a little bit of ARM at home. And thanks to that, we were able to do some early developments to develop few and to port a bit of code and try early some software stack. Then a little bit later, we had the Amazon Web Services that made the Graviton 2 and 3 available. And what's interesting with the Graviton 3, it's the exact same macro architecture in the core of the CPU. It's not the same memory stack, the same number of cores, but it is the same macro architecture. And then when NVIDIA released the Hopper and the superchip Grace or Grace Hopper, I mean, it was really efficient and many people could buy it and have it at home. That was not the case for Graviton 3, only in the cloud. And then the availability was much better and could experiment again further. So the goal was to evaluate several toolchains available on ARM, do the porting when needed, it was needed, and do some early performance assessments when it was possible, and it's not always politically possible to compare technologies like this. I will talk about the early access program at the end of the talk. It's a system that will be made available. Will be made available to all COEs to play with ARM system and continue the effort to port on ARM. So the result on this porting is that almost, except this field application, run on ARM. So we were checking the GCC toolchain mainly because it's best working, most compatible with all the applications. Except for also Tsunami High-C, where it's adaptive CPP, it's the open source version of SYCL, because they could not reuse the same font because of trademark issues, whatever. And we have some performance metrics for the IFS Dwarf, or the integrated forecasting system, that's also part of Work Package 3, Matteo mentioned it. Where we could evaluate on, I want to say, they are close in terms of generation. They came up almost at the same time frame. So the Zen 4 map architecture from AMD, Sapphire Rapids from Intel, and the Grace CPU from NVIDIA. They are almost the same size, from 56 to 86 cores, and the Grace is in the middle. And yeah, so the performance we can see is it's a relative performance. So it's sometimes the green win, sometimes the blue win, sometimes the red win, and it's okay, same order of magnitude, order of performance, it's fine. Except for this particular case with the Grace that's outperforming everyone with the ECR. It was because there was a memory allocation issue, and when you run on Grace with the NVIDIA toolchain, it uses a different memory allocator for the unified memory model, and it outperforms everything, and we were able to figure out how to optimize the code so that everything runs faster. So that was a nice story. So as I said, we had to bring some code out of the x86 ZOMA. You find a header, if define x86, do the code, else fail. I mean, pretty common in the code. We had to fix some build system, like the CMake. I mean, if there are some developers in the room, they know about the CMake build system. It has a feature to detect the compiler that is at use. And it was buggy for some ARM compilers, so we had to report bugs, fix it. Same for the library. I mean, OpenBLAS has been fixed for detecting compilers. FFTW has gotten some optimizations that come from EPI. It was part of Cypher's job to do that. We also see today better compilers. Cypher put some effort into improving the LLVM toolchain. Also brings a better performance for vectorization. We have contenders for the MKL mass libraries that are working now in ARM. So the ARM performance library was there already, but we have now the NVIDIA performance library that is even better and brings a lot of improvement for the performance. And we also have now better profiling tools that has been developed also as part of one of the French national projects. The tool Macao that has been mentioned in the COEs yesterday. Regarding the high bandwidth memory, the HBM, so we had to rely on the only available CPUs that bring some kind of similar memory subsystem. It's the Sapphire Rapid with HBM, the Intel Xeon Max. So they have I don't remember, like 64 gigabytes of HBM on the same package. So actually you can boot the CPU without DDR, just with the HBM on the package. And we were configuring those CPUs actually with DDR to compare HBM with DDR and leveraging some binding tools, especially in EUPEX, Work Package 5, as part of the software stack that was presented. There is a HW lock that's developed by Rhea Bordeaux. That is a tool that allows you to, tell to Linux to, okay, run this application on this core, but do the allocation of the buffer on this memory bank, and it will not get out. And it also allows to debug. So on the right here, you can see one screenshot, and I say it's just a random example to show the features. Execute on the green cores, so it's one NUMA node on the top left, but allocate buffer on the HBM on the bottom left here. It's completely inefficient, just to show what it can do. Okay, and again, we did some performance assessment on all the code. It appears that some of the code greatly benefit from HBM, up to 80% execution time improvement. So that's for Yambo here for Max. But also, depending on the application memory access patterns, sometimes you have no benefits at all, because it's mostly compute bound, and whatever the speed of the memory doesn't bring any benefits. So you can see, for instance, ExaHype with 0%, or here OpenGadget with 2%. That's some cases where HBM doesn't bring any benefits. Also, during this series, some teams have been going further. They have been developing some tools and methodology to not choose either HBM or DDR, but both at the same time to gain even further benefits. So that's on the bottom right, for instance, you see some work that has been done in Max, where they put some of the buffer on the HBM, some other on the DDR, and find a ratio of how many percentage of the buffer are allocated on the HBM on DDR, and you can see the speed up you get on the dots. And also Cypher is improving support within their compiler on the recent Ciconia library that was presented as part of EPI also, where you can tell directly in the source code with pragmas where you allocate the buffers and migrate buffers from HBM to DDR. So I was talking about HPCW that was developed in EasyWays. So it was released last summer, open source for the first version. Version 3 was the first open source release of HPCW. So it's a set of extracted application and dwarfs from the weather and climate domain. It's developed along with the developers of the applications, so that it's relevant for production. I mean, as long as they are not lying us or doing the property into putting the right code in the benchmark. It's realistic on near operational workloads. It is also fostering interaction outside of Europe within Hanami and Ganana, Japan and India, where new codes are being integrated into the benchmark. And it's also a vehicle for improving RISC-V support. I mean, also toward European sovereignty. BSC is working to port all the benchmark suite on RISC-V. So as part of EPI really, and there and all other projects. Okay, so if I would sum up the effort, nowadays, as I said before, ARMS is becoming competitive in the HPC environment. So we have cycles that will be coming this year, but we already have other contenders that have been proven efficient. EUPEX did lead the way into, paved the way for the COEs to prepare the codes for the ARM systems. And getting out of the x86 DOMA took some effort, but we did it in the end. All the code, except one that is partially just some patches to integrate, is working on ARM system, and the performance of SVE is actually on par with what we got on x86 with AVX. Most of the code, I mean, some codes benefit from HBM and some do not, depending on the application memory patterns. But two things to keep in mind. The HBM costs remain really high, so depending on what is your application set, you have to consider trade-off on this HBM. And as far as I know, after Rhea 1, I didn't see any CPUs with HBM in the roadmaps. GPU for sure, but CPU I didn't see. So we'll see what will happen with that. So the codes are ready to run on the first European sovereign CPU tailored for HPC, and we will actually make sure that this runs fine on Jupyter when it's available. Also, the domain-specific benchmark made it easier for us to deploy code because it integrates validation step, build step, and how to run it. So it's really convenient for porting and doing co-design to have such a benchmark. Okay, what's next? I was talking about the early access program.
Yeah, I think it's easy.
So during soon, I don't know the exact date. This person knows, maybe. The new system will be made available. It's under construction. It's delivered, but just some configuration to do, I believe. So it's made of 8 nodes with Grace CPUs. So it's available for all COEs and other European projects for porting code and play with ARM systems. Also, next is also better characterized energy. I mean, it's becoming more and more important for the procurement. The thing is, we are lacking, at the time, for now on the system we are lacking tools to properly measure energy across systems. Let's say I have a Grace system with actually air cooling fan systems. The system will report the energy for the fans as part of the system energy. On the other side, I have Intel water cooled. There is no energy for the fans, there is no fans. So I have a difference of 1 kilowatts for the fans that is not on them. I cannot compare. So we are lacking things to compare properly energy from different systems, and that's a bit blocking to better characterize. And of course, continue the efforts to port codes to ARM and Rhea and RISC-V to continue the efforts toward European sovereignty.
So yes, this is a slide that I had in your deck, Antoine. Basically, for the EAP that we are offering in EUPEX, we want to have your feedback if you are interested as a European project or a COE to have access to a Grace CPU nodes, because we plan to let users from the HPC community and just run jobs and try stuff on our platform. So please, if you are interested, or even if you are not, just let me know, because I want some feedback. Yes.
I'm from Xenagon and Hidalgo, COEs, and we are interested in having access to that.
Okay.
So
yeah, I will check your contact.
Yeah,
I
only
need to leave for the
clarify
airport
that.
in 15 minutes.
Yeah,
So.
Okay, but I will wait now.
Okay, so I have two aspects today because I'm EUPEX, but also representing cheese project and what back to and of course EUPEX is within this project because there is a 1.3 in which EUPEX and EUPilot are an integral part. So I mean we are strictly cooperating by scratch, you know, by default. So we don't need to do, oh, okay, this is granted. No? Because what packet 3 is EUPEX related images.
Okay.
I have 2 comments.
Yep.
In 2009, Spectrum 3D was used for the Aquila earthquake to give hints to the security civil Italian for replica. So it's not about it can be useful. It has been useful
No, yeah.
already.
Okay,
So
I misspoke then.
in 2009. So it was yes, a sad story for the Aquila, but a good story for. And second, if you say you cannot compare.
It's difficult to compare.
Yeah, but the thing is, if you can make a differential for improvement, never mind if you cannot compare in 2 machines. If you do some improvement, if you have a clear view on 1 machine, you can have what is the benefit of your action. So even though it's not comparable, there is usefulness.
Yeah, you can optimize one application on the same
Right.
machine and compare 2 runs on the same machine and say, okay,
Exactly,
this run
exactly.
consumes less energy. Yeah.
Exactly.
And what would you like to have as a feature, I would say, to be able to compare such system? Do you need precise power consumption per subcomponents?
Yeah.
Do you need stuff aggregated at the
So
size of the rack?
Even if the probes or the sensors actually measure different things, if we have the documentation of what they are measuring and how they behave, that will actually already help. But usually you have just, okay, this one is consuming 1 kilowatt and this one is 2 kilowatts.
Okay.
Is it the CPU, the memory, the NIC, the I/O, the switch, the cooling? You don't know.
And you cited, you used the example of water-cooled versus fan-cooled, air-cooled. If you have the power consumption of, I don't know, the pumps and all the system for water cooling, could you aggregate all your data to racks and try to see not per node but consumption per racks? That's something that would be useful to you?
The system consumption could help, but it's again, I don't know if it's a decidable problem because you have one job that will run HPL and the other one will run IOR. It's a IO benchmark. So HPL will not use the storage at all. It will just use the CPUs and the memory and the NIC a bit. And on the other side, you will have IOR, which will be hurting the file system through the IO, through the network. And do you impact the consumption of IOR on HPL IO consumption? I mean, you need more data than just the whole system consumption. So that's probably some research on new idea to get and to improve reporting on the job consumption.
And would you be able to make kind of a wish list of what you would like?
Maybe, yeah.
I want to participate in the list.
Not that we can make it happen, perhaps we cannot make it happen, but if we have feedback and co-design possible.
Oh, great.
Yeah.
Yeah.
Great, thank you. Thank you.
Thank you very much.
Thank you so much.